Assalamualaikum warahmatullahi wabarakatuh. We're from Section 1, Group 9, and we will present our Chemical Engineering Thermodynamics project. The topic is Flash Separator Design for Chloroform and n-Heptane. And this is our team members, including me, Nada Sondus, and Nur Aina Batrisha, Lee Sun Sen, and Ku Yu. What is flash separator? A flash separator, also known as a flash drum or flash vessel, is a process equipment used in the oil and gas, chemical and petrochemical industries to separate a pressurized stream into vapor and liquid phases. It is an important unit in the natural gas dehydration process, where it removes gas and condensed hydrocarbons from the glycol absorbed in the contact tower. Desperation occurs through a process called flashing, in which liquid hydrocarbons rapidly vaporize when the pressure is reduced from a high pressure condition to a lower pressure. As a result, the flash separator efficiently separates the stream into its liquid and vapor components under steady state operation. The objective of this project is to design a flash system for separating a binary mixture of chloroform and n-Heptane. Second, we need to perform flash calculations to determine the moles of liquid and vapor phases, as well as the liquid and vapor mole fractions of the chloroform and heptane mixture.
Alright, so let's move to real life application. First, a flash tank separator is used in the oil and gas industry for glycol dehydration, and it separates absorbent gases like a methane and other impurities from rich glycol before the regeneration process. So basically, methane is known as a more volatile component, and other impurities, which is liquid, is known as a less volatile. So more volatile goes to the top stream, and less volatile goes to bottom stream. And second, the separated gas can be recovered or used as a fuel instead of being released to the atmosphere. These help reduce the emission and improve the efficiency of the system. So knowing as more volatile component is knowing as a power greenhouse. So when we are use it, it help reduce the emission. So while the glycol is and then the part which is a less volatile, which will be regenerated and reused. So let's move to one of example. In a real life industry, we can find out the image. So here are the real applications that we can find out in the industry.
For the calculation, firstly, we need to do assumptions. So we assume that the mixture is an ideal solution. And for the basis, 1 mole of mixture is fed into the flash separator. And for the condition, by referring to table B1, boiling point of chloroform is 334.3 Kelvin, which is 61.15 degrees Celsius, and for the boiling point of n-Heptane, which is 371.6 Kelvin, equivalent to 98.45 degrees Celsius. To ensure the effectiveness of the separation, the operating temperature must be between the boiling point of chloroform and n-Heptane. Therefore, we chose 80 degrees Celsius, which is 353.15 Kelvin, as the operating temperature. And for the pressure, we chose 1 atm, and for the mole fraction of chloroform, Z1 is equal to 0.5, and also for the mole fraction of n-Heptane, Z2 is equal to 0.5. To calculate the saturated pressure P set, we use the n-Heptane equation, which is ln P set in kilopascal is equal to A minus B divided by T temperature in Kelvin plus C. So referring to table B2, the constant for n-Heptane equations are as follows. By plugging the constant into the n-Heptane equation, we can get the saturated pressure for chloroform P1 set is equal to 180.4394 kilopascal, while for n-Heptane, the saturated pressure P2 set is equal to 57.0866 kilopascal. To calculate the bubble point pressure P bar, we use the equation P bar is equal to x1 P1 set plus x2 P2 set, and eventually we can get the P bar bubble point pressure is equal to 118.763 kilopascal, while for the dew point pressure P dew is equal to 1 over y1 over P1 set plus y2 over P2 set, and eventually we can get the dew point pressure is equal to 87.8416 kilopascal. Since the pressure we chose 101 0.325 kilopascal is in between the dew point pressure and the bubble point pressure. Therefore, two-phase flash exists.
Next, we are going to calculate the equilibrium ratio Ki by using the equation Pi saturation divided by the P. So for the Pi saturation, we already calculated just now using the n-Heptane equation. And for the P, it's just the initial condition we set is equal to 1 atm, 101.325 kPa. By substitute all the value, we get that the K value of chloroform is equal to 1.7808 and for n-Heptane is equal to 0.5634. So a K value greater than 1 is indicate that the component tends to enter the vapor phase, while the K value less than 1 is indicate that the component tend to remain in the liquid phase. Therefore, the chloroform is more volatile and preferentially enter the vapor phase, while the n-Heptane is more concentration in the liquid phase. Now we are going to calculate the mole of vapor V by using the retrograde equation, which is the summation of ZiKi over 1 plus V multiplied Ki negative 1 is equal to 1. So the K is just the fixed composition and the K is the equilibrium ratio we calculate just now. By substitute all the value, we get that the mole of vapor is equal to 0.5048 mole. So since the basis of calculation is 1 mole of feed, so the mole of liquid L can be calculated using L is equal to 1 minus V. Then we get that the mole of liquid is equal to 0.4952 mole. This means that approximately 50.48% of it leave the flash separator as vapor, while the 49.52% leave as liquid. After determining the vapor and liquid amount, the liquid phase mole fraction Xi can be also calculated using the flash equilibrium equation, which is Xi equal to Zi over 1 plus V multiplied Ki negative 1. By substitute all the value, we can get that the liquid phase mole fraction of chloroform is 0.35x6, while the liquid phase mole fraction of n-Heptane is equal to 0.6414. Since we know that the total mole fraction is equal to 1, we can also use the automatic method, which is 1 minus mole fraction of chloroform to get the mole fraction of n-Heptane. Both method will give the similar answer. This result indicate that the liquid stream contain a higher concentration of n-Heptane. The vapor phase mole fraction is then calculated using the relationship yi equal to kixi. For the chloroform, we just substitute the value and we can get the mole fraction is equal to 0.63x6. While for the n-Heptane, we can just use 1 minus y1 and we can get the vapor phase mole fraction is equal to 0.3614. By comparing the liquid and vapor composition, we can see that the chloroform is enriched in the vapor phase while the n-Heptane is enriched in the liquid phase.
To conclude, the flash separation analysis of the chloroform and n-Heptane measure demonstrate that vapor-liquid equilibrium can be achieved at 353.15 Kelvin at 1 atm. So the calculated vapor fraction is 0.5048 mole and the liquid fraction is 0.4952 mole. Due to its higher volatility of chloroform, which is chloroform is enriched in the vapor phase like I mentioned in real-life applications, top and bottom stream, whereas n-Heptane is a congruent in the liquid phase which is known as less volatile component. So the result confirms that the flash separation is an effective primary separation technique that can reduce the load of downstream purification unit that can improve overall efficiency.